So before going to the reactions, as we discussed in the last class, that the nature of a carbonyl group is okay. Carbonyl group. The carbon is an electrophile, and oxygen is a nucleophile. So why carbon is an electrophile? Because of the higher electronegativity of oxygen and the possibility of resonance, okay, that we talk. Now, if any group is present here that can donate electrons, these, then it means it will decrease the electrophilicity of carbon. Okay? If they are able to withdraw electrons, they will increase the electrophilicity of carbon. So here hydrogens, they are considered as neither electron donating nor withdrawing. Okay? So now this carbon, if you have, and if you compare this one with one methyl group, okay, like this one here. So this carbon here, it is has a pi bond, so the adjacent methyl group can donate electrons by hyperconjugation, okay, that we have discussed previously. So one methyl group electron donating, that will neutralize the positive charge on carbon, that will decrease the electrophilicity of carbonyl carbon, okay. So now if you have a nucleophile, so this formaldehyde will be more reactive than acetaldehyde. Why? Because in acetaldehyde there is a methyl group present. So both these are aldehydes. Now if you compare this one with another acetone, so acetone has two methyl groups, so even more electron donating groups are there. So that will neutralize the positive charge on carbon even more. So it means that will decrease its reactivity towards an electrophile. Okay, so these are three examples. So it means that for a nucleophile, formaldehyde will be more reactive than acetaldehyde, and acetaldehyde will be more reactive than acetone. Okay. Now, if you have, let's say, aromatic aldehyde, let's say benzaldehyde, okay. So what about this phenyl ring, whether this one is electron donating or electron withdrawing for the carbonyl? So here it's the different factor it works, okay? So note the hyperconjugation. So here the factor is resonance. See this one, this can go here, this can go here. So it means the double bond is coming, that will even neutralize the carbon even more. Okay, so higher electron density. So you can write this resonating structure. And this one you can write further all these resonating structures. So it will be a positive charge here. Okay. And this can go further. So it will be here, positive charge. Okay. Now this can come here, and this will be So this will be the this final resonating structure. Okay, so these are the resonating structures. So it means so resonance, see, it is direct movement of electrons. So it will be, this carbonyl will be least reactive among all these four. Okay, so aromatic aldehydes are less reactive than even aliphatic ketones and the other aldehydes because of the resonance. Now, if you so any group now come in the this for aromatic aldehyde. So any group present electron withdrawing groups in the benzene ring will increase the electrophilicity of carbonate carbon. Okay, let's say here nitro. Okay, at para position, C para position has a positive charge. If it will have nitro, it can even more withdraw the electrons from this carbonyl. Okay, so among aromatic aldehyde, this will be more reactive. Okay, then if it is present at the meta position, here. Okay, why meta position will be less? Because at meta position, see this, there is no positive charge in any resonating structure. So the resonance by nitro group will not be effective at the meta position. Okay, that we have discussed this on in chapter 15 and 16. Okay, at meta position. And so it means this will be, but here nitrogen will be still effective via inductive effect, because nitrogen and oxygen, they are electronegative elements, so they can withdraw electrons via a sigma bond, via inductive effect. Okay, so that will make this one more electrophilic than the just benzaldehyde. Okay, so this is very important. So try to understand the trend and the reasons behind that. Okay, so two things: hyperconjugation and the inductive effect. Actually, three things: resonance, inductive effect, and hyperconjugation. Three important concepts behind the reactivity of these carbonyl compounds. Okay. So what does it shows that nucleophile can react with the carbon of the carbonyl, and that is so that's why formaldehyde is very reactive. So what are the nucleophiles we will study? See, just all nucleophiles will react in the same ways. So nucleophiles will talk, if the nucleophile is negative charge, we will talk hydroxide ion, alkoxide ions, and then hydride ions, and carbon nucleophiles. Okay, so both all these reactions we have discussed before. Okay, and then if the nucleophile could be neutral as well, not negative charge, so they are less nucleophilic, like water, alcohols. Okay, and then comes nitrogen nucleophile. Nitrogen could be in the form of ammonia or amine. So we'll talk all mostly primary amine and secondary amine. They will react in a different ways. So if you understand one basic mechanism, okay, you can understand all. So how these nucleophiles will react, okay? So that we have discussed. So suppose if you have a carbonyl compound, I'll put both side R, and the nucleophile, because it's electron negative, it will go to the carbon, this will go there, okay? The pi bond on oxygen. So this will be added, and it will be O minus, and this O minus will take proton from the acid, and that will give the sp3 hybridized final molecule. Okay, so this is the product. So same nucleophile O minus or R minus. So those will so here, see nucleophile, you can take OH or R or H or carbon. So here important, what is the, how do we get um, hydride nucleophile? Anybody from the last lecture? How do we get a hydride nucleophile? No? There are two sources we have discussed hydride nucleophile, that sodium borohydride, okay, or lithium aluminum hydride. Either one you can use for aldehyde or carbons, okay. The only difference, sodium borohydride is mild and lithium aluminum hydride is very strong. Then you will work up with an acid, so it will be reduced. Okay, one hydrogen will come with the hydride and it will take the proton from water. Okay. So what is the source? So this is in short. What are the sources of carbon nucleophile? What is that? What we have discussed carbon nucleophile? Hmm? See this thing should be in your fingertips. If not in fingertips, it should be in your lips. Okay. This because we have talked many times this carbon nucleophile. So just if you know, just talk. So that will remove if your tardiness when you sleepy or anything. Okay. So the only one that so far we have discussed is Grignard reagent. Okay, this is the carbon nucleophile negative charge. So see here, carbon nucleophile, all the different Grignard reagents they work, and after acid work, you get an alcohol. Okay, so these are the reaction of this one. A new nucleophile today we'll talk, carbon nucleophile that we have not discussed before, and this is very important. If you guys have already done organic 2 lab for this week or next week, we'll do, that is the lab as well. So if you guys are in my lab section, I will send you guys a video related to Wittig reaction in the lab section, okay? So, see, generally, very brief, if triphenylphosphine, okay? So here, so phosphorus is a lone pair, okay? So if you'll see the periodic table, phosphorus is below nitrogen, okay? So it will behave as a nitrogen. The only difference is that it is less electronegative. So less electronegative means more nucleophilic. Okay. So this is the triphenylphosphine, very good nucleophile. Okay. In short, we'll write this one, PH3P. This one. So PH3P, when it generally if you take alkyl halides, so it's a very good nucleophile in the lab. we'll go with a specific example. If benzyl chloride, okay, other, this is benzyl chloride. So see, this is a primary carbon, so it's a very good electrophile for SN2 reaction. So it removes the chlorine. Okay, so we'll get PH3P positive, and you have a carbon. I'm writing the hydrogens on carbon and pH for phenol. Okay, like this one, and chloride ion. Okay, so this will be called benzyl triphenyl phosphonium chloride. Okay, so these hydrogens are acidic here. Okay, so when you take a base, generally strong base is required for this. So in the lab, you guys will do sodium hydroxide is also strong. So it will take this proton, okay, and then this will go on this. So what will be the product? So you'll have a PH3P carbon, here negative charge, hydrogen, pH plus water, H2O plus sodium chloride. Okay, so this is the product. So this formation, now you can write here as a resonating structure, this one. So PH3, P double bond, CHP. See, phosphorus now here has a 5 bonds, and that is possible because it has d orbital. Okay, so this resonating structure, and this is stable. So here you see this negative charge, these are called aldehydes. Aldehydes. There's such type of general structure. Okay, carbon negative and phosphorus here positive. So this negative charge, this is a very good soft nucleophile. Okay, at the end of this chapter, we'll talk about soft and hard nucleophile more. So just now remember soft nucleophile. This can react with the carbonyl compounds. Okay, so now here I'm writing, let's say if you have this benzaldehyde, and either this one or this one, this is called Wittig reagent. So this is very important. George Wittig discovered this one in 1960s, and he got Nobel Prize for this one in 1974. So now you can understand the importance of this reagent, and it's still more than almost 50 years, and it's still widely used, this one, industrially and in labs to make different products. Okay, particularly to make different types of drugs. Okay, so this reagent, when you react with PH3P plus, I'm writing the ionic form, so CHPH here, negative charge. Okay, the same, this one. So this carbon is a nucleophile, so it immediately reacts with the electrophilic carbonyl carbon. Okay, so now again, so PHO minus here, see the product, and I will write little bit rearranged again. Okay, so PPH3 plus, here you'll have hydrogen and pH. Okay, just the nucleophile. Okay, Now this negative charge, see, and positive charge, they are very close, very easily they can react. So it will make a four-membered ring. Generally, four-membered rings are not favored, but in this case, because phosphorus is a big size and it forms easily. So like this. Okay, carbon, phosphorus. So it's a four-membered ring. Okay. So this is called betaine intermediate. Betaine. Now, if you can recall, it's like a retro-Diels-Elder reaction. So what happens? This can go back here, and then this bond will come here. Okay, the carbon-oxygen bond will be broken, and phosphorus-oxygen double bond will form. Carbon-phosphorus bond will be broken, and carbon-carbon double bond will form. So yeah, not to mention here you have a hydrogen. Okay. So this will be, so what you will get, pH, carbon, here hydrogen, double bond, carbon, okay, pH and hydrogen. Okay. So this is the final product. And the byproduct of this reaction is phosphorus double bond oxygen and triphenyl phosphine oxide. Okay, so this one triphenyl phosphine oxide, and the product is carbon-carbon double bond oxygen. Okay, so what is the overall reaction in this? If you will see carefully, the overall reaction, see, easy to remember, the oxygen goes with triphenyl phosphine as triphenyl phosphine oxide, okay, and the carbon, that carbon-carbon go, this part, it goes with the carbon nucleophile to make the olefin. Okay, so it is just a kind of simple exchange with that triphenyl phosphine and oxygen will go, and this carbon-carbon double bond will form. Okay, any question? Okay, so I will give you guys one more example here. I will write directly the Wittig reagent. Okay, so pH3P double bond. Now, if you have just this one, okay, methylene carbon with two hydrogen. In the last example, one hydrogen was replaced by phenyl. That was the example. So what it will form when you react with this, let's say, just simple cyclohexanone. What will form? See, what did I show you guys? That triphenyl phosphine will go with oxygen. Okay. So the remaining part is here. You will have that cyclohexane double bonded with carbon with two hydrogen plus a triphenyl phosphine oxide. Okay. So here, this so easy. You can see this one. Okay. Now, if you are given an olefin, okay, let's say if you are given an alkene, then retro, how will you go backward? Suppose if you have this alkene, here you have pH and pH, How can you go backward? That what was the Grignard reagent used to make this one? Okay, so easy, you can see here, right? So you can take pH double bond OPH plus pH3 P double bond. This was a Grignard reagent. Okay, so this is the Grignard reaction. Okay, any question? Okay, now let's come back as I discussed in the first slide that the nucleophiles could be negatively charged or there could be neutral species. Okay, see this one here in the very first slide. So now let's talk more now about the neutral nucleophiles. Okay, so neutral nucleophiles, they react with the like formaldehyde. Okay, if you add water in this, it will completely dissolve. Okay, it will mix with water. So what happens? How water it reacts with formaldehyde? See, as I said, formaldehyde is one of the most reactive aldehydes because there is no electron donating group to neutralize the carbon. So what happens immediately? This will react, okay, in water, and it's a reversible reaction kind of. So this will be O minus hydrogen, hydrogen, okay, and here you have oxygen, and because you have the water medium in there, this one, so O minus can take proton from another water molecule, okay? And one water molecule can take this proton. Actually, it is just exchange of protons. So this one will be hydrated. What is name? Hydrated aldehyde. So this C water, OH and H water was added. Okay. So this you guys will see everywhere. This one on campus, this formaldehyde. So 40% formaldehyde in water. In water, it makes formalin. Okay. And formalin, have you guys seen formalin? Formalin is a preservative. It's widely used to preserve living tissues. Okay. So whenever you see wherever a snake in a jar, okay, dipped in some kind of liquid, that liquid is a formaldehyde, and that is in this form. Okay, so any aldehyde will react like this. Okay, but other aldehydes, like if you have benzaldehyde, here this one, if you mix, although the reaction is reversible, but this product is more than 99%. Okay, but if you take benzaldehyde, as I showed you guys, that because of the resonance, aldehyde of benzaldehyde, this carbon is less electrophilic, so it will react the same way. You can write the mechanism, okay? But the hydrated product will be much less than the unhydrated product, okay? Not even, maybe less than 0.1%. Okay. because of the less electrophilicity of the this one of the carbonyl carbon. Okay, any question? Similarly, alcohols can react, okay, and they are useful, very useful material they make. So if you have an aldehyde or ketone, let's say this one, okay, and you take neutral molecule methanol, right? In the presence of an acid catalyst H plus, like this acid catalyst it is called PTSA, para-toluene sulfonic acid. It's a sulfuric acid derivative. So see, this is called PTSA, para-toluene sulfonic acid, OH. Okay. So here it is OH, this gives H plus. So what happens, see the oxygen is nucleophilic, okay, is a base. So first oxygen reacts with this, the acid catalyst, okay. So what it will form? It will form oxonium ion. This oxonium ion become, oxygen is by itself more electronegative than carbon, but this oxonium ion even becomes more electronegative, and that withdraws this double bond pair towards itself, and this carbon becomes more electrophilic. So what happens then? The next step, methanol reacts. Okay. So methanol will react, and these reactions are reversible. So methanol will react. So what will be the product? So you will have OH, and here you have OCH3, because that bond formed by this oxygen will get positive charge, this one. Okay. Now the next step, this OH will be taken by the solvent or the conjugate base, and it will make this neutral molecule. Okay. So see this one, and remember this one here. This carbon has two functional groups. Let's see this one. One is ether and another is hydroxy. Okay. So when the same carbon has ether, oxygen attached at ether and oxygen attached at hydroxy, that is called hemiacetal. Hemiacetal. Okay. Remember this one, the term hemiacetal. We'll talk later about hemiaminal as well. Hemiaminal. Instead of oxygen, it will have nitrogen. Okay. So this one. Now again, see this OH gets again protonated by the catalyst. Okay. So what it will form? OH2 plus OCH3. And as you know, as soon as oxygen gets protonated, it becomes OH2 plus, it becomes a very good leading group. So this will come here and this will leave in the form of water, H2O. Okay. So what it will form? It will form positive charge. Okay. So far, what are you seeing? This one here. This oxygen is replaced by this oxygen. Okay. That here this it formed. And this oxygen positively charged is very strong electrophilic carbon here, this one, that reacts with another methanol molecule. Same as the beginning. See, this one is, you can compare with this step. The only difference is that here now instead of hydrogen, you have CH3. Okay. So what it will form? It will form this OCH3 and OCH3H. Okay, this you can compare this structure with this one. Okay, OCH3. Again, the solvent or water molecule will take this proton and this will form two oxygen attached CH3OCH3. Okay, so this is this is their neutral oxygen. That's how it works, and this is called acetal. This functional group acetal. What is acetal? Carbon attached with two ether oxygen. Okay, remember this one. If a molecule is given, you should be able to quickly identify this hemiacetal or acetal. Okay, so this is the synthesis or mechanism for the formation of acetal functional group. Okay, I will give you guys one very practical example. So these are very, very important. Okay, all carbohydrate molecule that we take in the form of food or they are in the plant in the form of cellulose polymers, they are the hemiacetals and acetals. Okay, that's why this is very important. You guys will see a lot in biochemistry. Okay, so see, this is the structure of glucose. So glucose is actually an aldehyde, okay, like this. Okay. Here you see that there is a carbonyl group and there are so many OHs. Okay. So you have seen in this previous slide, say carbonyl group react with OH to make hemiacetal here and further reaction with acetal. So this one here immediately here this and reacts like that way. So this is the example of intramolecular hemiacetal formation. So after the proton transfer, same as this proton transfer, okay, it forms this cyclic structure type. So it will be OH, see this will be ether, okay. So all the glucose, it has an aldehyde functional group, but it exists as a hemiacetal. See this group here, hemiacetal. If you compare this one here, okay. So this hemiacetal, they react, okay, together, um, like this one here. See this, if it take another glucose molecule, let's say that this, suppose that this one or this OH, okay, it will react here and this will leave for further reaction to make acetal formation. So what happens? It will form like this. Okay. So this one here more as this. So this is the, so that's how they polymerize. It can keep on reacting with this, and that's what they make cellulose or starch or glycogen. All these polymers, they react and they have what is this one? See, this is acetal functional group. Okay, this side it can further react with another hemiacetal. So that's how they make the polymer, different polymer chain reactions. Okay, any question? I hope you guys are understanding this. So first try to understand this basic mechanism, okay? Then only you can understand these complicated structures. Okay, let's come to the nitrogen nucleophile, okay? In the last class on Tuesday, we discussed about the nitrogen nucleophile. So we'll talk more detail about that one. So nitrogen nucleophile here. So if you have cyclohexanone and this you take ammonia, okay? Exactly whether you take ammonia or you can replace one of the hydrogens with R, primary amine, okay? So this one will react the oxygen, okay, to make so what it will be O minus this one positive, okay, and this bond will break off one of the hydrogen. Another ammonia molecule or a base can take, or the conjugate base can take this proton. So what it will happen, and the oxygen can be protonated, so it will be OH, and you have M, H, this one, okay? This group is called hemiaminal. Hemiaminal. So remember, So two ethers were, one ether, one OH was hemiacetal. Here one OH, one amine, carbon nitrogen single bond. This is called hemiamino. Okay. This reaction gets accelerated by a mild acid. If mild acid is present in this, like H plus, very little acetic acid, or like, yeah, acetic acid is a weak acid is present. So what will happen? First, the lone oxygen will get protonated. Okay. So I'm writing this way here. Say acetic acid is present. Here I will write, so what will happen? It will, just like the previous example, first it will form oxonium ion type intermediate, okay? And then this nitrogen will react. Here the reaction will be faster because the carbon of this carbonyl, oxygen carbon, is more electrophilic. Okay, because the positive charge on oxygen. So what you will get? You get OH and nitrogen. Okay, the proton can be taken by the conjugate base or the solvent. See here, if you take acetic acid, then acetate ion will be the conjugate base. It will be taken. So acetic acid will be regenerated. So that's why you need catalytic amount that will give this product. Okay. Again, same thing, that again this OH will be protonated. And as soon as OH gets protonated, it forms OH2 plus, that becomes an excellent leaving group. Okay. And the lone pair also, it pushes out the water molecule. So the product will be nitrogen. Okay. And then again, this one of the protons will be removed, and this will form carbon nitrogen double bond, and this is called imine. Remember this imine, or that when it that imine forms with the imine, when they make the with amino acid, that is called Schiff's base. Okay. So this is the mechanism for the formation of carbon double bond nitrogen. Okay. So what is the overall reaction? See, overall reaction, if you will see at the beginning, that oxygen and two hydrogens are gone in the form of water. Where is that water? This water. That will be gone. Okay. So, so the overall reaction you can easily write here. See, that two hydrogen of amine, ammonia, it is gone in the form of water, and it formed like this, plus H2O. Okay, in the presence of acid catalyst. Now this hydrogen can replace with different things. See, because just you need two hydrogens. So if you replace that hydrogen with an R group, means carbon, okay, then it becomes primary amine, then you can make just carbon double bond nitrogen and R group. This is the imine of an alkyl group. If you replace this hydrogen with another NH2, okay, then this one is called hydrazine. Okay. So what will happen? Just one will react. So you will get another one will be free. That can react again with different ketone, but remember this one. So this hydrazine, when it makes a double bond, like here amine becomes imine, okay? Here hydrazine, this product is called hydrazone, okay? If you have that, this hydrogen is something else like H2O, NH, you can more attach something here, OCOR, like this type, okay? Here now the whole, this group H is this part. So this nitrogen will not react because it is sterically hindered, this nitrogen. And it has a carbonyl group. So only this nitrogen will react, and the reaction will be same, that oxygen and H2 will be gone in the form of water. And so what will be the product? Nitrogen, another nitrogen is, okay? This whole such type of molecules are called semi-carbazide. Okay? So the product will be called semi-carbazone. Okay, so all those simple reactions that makes, the reaction is similar but makes different product. I will give you guys one example that we do this reaction in our lab to make compounds that are very good against drug-resistant bacteria. See this. So don't worry about the big structure. You can write. So here, generally this halogen or fluorine, chlorine, or CF3, anything, and here we have aldehyde, okay? And this we take, here we have this again phenyl and carboxylic group. Say this is a big structure, and this is called pyrazole, okay? When we react with hydrazine derivatives like H2 and nitrogen, and with the hydrazine, here again we attach the phenyl group, okay? And here let's say fluoro. Okay? So what will happen? The reaction, don't get scared by the big group, just focus on the functional group that will react. So what is the reaction we did? We did that oxygen and this H2 will react, will go away in the form of H2O. So the product will be So nitrogen, see these things you will not find in the book. These are the research. If you see in front of my lab, we have that papers on the wall. You can check. So this hydrazone. And these hydrazones are very active against Acinetobacter baumannii. This bacteria is considered the most dangerous bacteria, drug-resistant bacteria in the hospital infections. Okay, so what is the basic reaction here? See, the formation of carbon-nitrogen double bond. Okay. And when we do the same reaction with anilines, okay, NH2. So what will happen? NH2. Again, the same thing will happen. H2 will be gone and oxygen will be gone in the form of water, and it will make a double bond. So the product will be okay. Here the product is imine. Another reaction, you guys remember this one. I will write in the previous slide. When imines, like see this imine, carbon nitrogen double bond, are treated with sodium borohydride. Other reagents are also there, but you guys just remember sodium borohydride. So what will happen, like that carbon oxygen double bond reduction by sodium hydride, that pi bond is reduced to an alcohol. Similarly here the pi bond will be reduced and it will make NH. So the product will be NH2 reduced, amine. So imines are reduced to amines by using sodium borohydride. Exactly the textbook reaction we do, that here we use sodium borohydride and this imine is reduced to an amine. See, all other things will be same. Okay. What is reduced? See this carbon, the carbon double bond nitrogen is reduced to that hydrogen. So this is the amine reaction. So these are the different reactions with nitrogen nucleophile. Okay.
What about the carboxylic acid at the end? How come it doesn't react with that? Because it's carboxylic acid.
Yeah, so good question. So carboxylic acid, do the carboxylic acid, this is the called Michael addition. Okay. Michael addition, or another name is, this is called conjugate addition. Or also it's a 1,4 addition. Okay. So if you have this one here, carbonyl group with adjacent carbon double bond, okay, here. So if you guys remember that if there is a functional group adjacent carbon is called alpha, then another carbon is called beta. So this is called alpha beta unsaturated. Unsaturated means that alkene, unsaturated carbonyl. If you take hard nucleophile, okay, as I said at the starting of this class that we'll talk about hard and soft nucleophiles. If you take hard nucleophiles, then it will go here. Okay? The best example of hard nucleophile, let's say Grignard reagent, okay, CH3MgBr. And soft nucleophile is this one. Gilman's reagent. Can you guys recall Gilman's reagent? Chapter 11. Okay. So Gilman's reagent, see here, magnesium is a strong metal, see group 2 element. Okay. And copper is a metallic character compared to magnesium is very less because it's in CD group, less high electronegativity than magnesium. So magnesium donates the electron very more on this carbon. So here the negative charge is more. Okay. So when the negative charge is more, that makes this one a strong nucleophile. A strong nucleophile means that hard nucleophile. Here, this is because the copper electronegativity is more or it has less electropositive character. So this one is a weak nucleophile. More than weak, here it is the term is used soft nucleophile. So soft nucleophile will go here, then the pi bond will go here, and this will go here, will move. That is called the conjugate reaction. Okay, so let's go first the Grignard reagent. So what will be the product? The Grignard reagent, you guys know, will be that CH3 will be added here. Here will be O, MgBr. Okay. So let's say it's a tentative just numbering. It is not the nomenclature numbering. So this is oxygen 1, 2, 3, 4. So what did we find? That this counter ion is going at 1 and the methyl is going to at 2. So this is called 1,2 addition. This is called 1,2 addition. And now if the copper, what will happen? See this one. I'm writing the resonance structure of this. You see here the resonating structure. So first resonance, you can write like this. Positive charge, then here. See here, oxygen negative charge, okay? This one will come here, then another resonating structure you can write. Here, this one, O minus. Okay? You guys see this one? So here, this positive charge is more positively charged. Why? Because it has the adjacent oxygen. So the strong nucleophile will go to the strong positive charge, and this is the weak nucleophile will go to the weak positive charge. Why? Because this is away from oxygen. So this nucleophile will come here. So what will be the product here? O minus, lithium will go, lithium positive here, and copper CH3 and CH3. Okay, you guys see this one? This is called 1,4 addition and or 1,4 addition or Michael addition. Why? It is added to 1, 2, 3, 4. One fragment at 4 and another fragment at 1. Okay, so this one, then see this methyl group is transferred here. So this will form here the methyl group, and when we work up with an acid, this takes a proton, so it will be OH. Let's say this, and this will undergo ketoenol tautomerism. Again, you guys will have to recall chapter 9, ketoenol tautomerism. Will make this ketone here. So overall, what we see, the methyl group is added here, and the methyl group is added here by the soft nucleophile. Okay. Okay, guys. So this is finished. So this is a long chapter. So okay, prepare well for this one and the preview of the carbonyl compound for the quiz on Tuesday. Okay.